So this is a very short course on software engineering, and the content has been taken from a very good material made by a world famous renowned H.V. Blight, and all thanks and credit to him. So let us start. This is Ariane Flight 501. So what happened? It disintegrated after 39 seconds. This was a prestigious and valued flight. This was caused by large correction for altitude deviation, and it was caused by the wrong data which was being sent to onboard computer. This is caused by software exception, software fault, error, bug, or any word you can use here in inertial reference system after 36 seconds. The details: overflow in conversion of variable from 64-bit floating point to 16-bit signed integer. This was the cause. There was an overflow. So of the 7 risky conversion, 4 were protected. This was not. The reasoning was it was physically limited, or large margin of safety can be considered. But in case of an exception, it should report full failure on databus and should shut down. The explanation of this loss or this catastrophe was inadequate testing, the reuse problem, that is the wrong type of reuse, and the design, that is the philosophy employed for design, was not up to the mark. What about inadequate testing? Say specification does not contain Ariane 5 trajectory data as a functional requirement. Was it there? Was it not? And in test, the SRIs, that is the component that measure altitude and movement of the launcher, SRI, were simulated by the software modules. Improper use, that is, if a component works perfectly well in one environment, will it work in another environment also? It doesn't necessarily do so in another. So Ariane 5 is much faster than the Ariane 4, and the horizontal velocity builds up more rapidly than Ariane 4. So excessive values for parameter is in question, and this wish for quick alignment after hold in shutdown can we assume it. So this software runs for a while after liftoff. It doesn't have any purpose for the Ariane 5, but was still there. What about wrong design philosophy? If something breaks down, such is caused by a random hardware failure. What is the action? You need to shut down that part right there. So there is no provision for design errors. Now let us talk about the software engineering, how it began. In 1968-69, NATO conferences were, they were organized. So this introduction of the term, or the coining of this term, software engineering, took place. So the idea was software development is not just an art. It's just not some trick, but we need to build software just like we build bridges. We build any engineering masterpiece. The current status is we have achieved a lot, but some of our bridges, they still collapse. This is Tacoma Narrow Bridge, just for example. After some time, it happened like this. This is the relative distribution of software and hardware cost, right from 1955 till 1985. So now the percent of total cost with respect to the time, this is hardware cost, development, software, and maintenance cost. So still in this time, the maintenance cost is increasing, the development cost is also increasing, and the hardware cost is decreasing. So we need to ponder upon some points. Why does this software maintenance is costing so much, as we have seen just in the figure? This is the relative distribution. Okay, so we need to understand why maintenance is taking so much of time. Was not the software built properly at the first go? Why would it require maintenance? Well, the maintenance is necessary. IEEE definition of our software engineering is: software engineering is the application of systematic, disciplined, quantifiable. See again, systematic, disciplined, and quantifiable approach to the development, operation, and maintenance of software. That is, the application of engineering to software. In one line, you can say the application of engineering principles to the software engineering, but applying the systematic, disciplined, and quantifiable approach, which we generally apply in normal, like civil engineering, we apply it for the development, operation, maintenance of something. Then this is what IEEE has to say about software engineering. There are various central themes. Software engineering is concerned with big programs, large program. We are often concerned about the complexity of the software and how the software evolves right from the inception till it is delivered. And development needs to be very efficient. So you are doing it together. Software must effectively support the user. It involves different disciplines, and software engineering is a balancing act. Building software, which is equivalent to our building bridges, yes and no, because software is logical. It is not that much physical like hardware or building bridges. That is why there is a difference. So progress is not easy to see. It is hard to perceive. So speed will not be equal to the progress. Software is not continuous. You cannot just employ certain manpower to make bridge and try to define or find out in these many days this part was completed, in these many days these parts were completed. So life cycle, simple life cycle model which a software adopt is, you have a problem, you are presented with a problem, or you have to solve certain problem, then the requirements is gathered, that is requirement engineering is done, the requirement specification is created, then you go to the designing phase, you design, then you try to implement this design in the form of a system, that is you code, then you test the system you have made. Once you have tested it and you are confident enough to call it as a working system, then you go deliver it and you go to the maintenance part. The other point is this a good model? And off we go about how we are going to go about it and how we should go about. How we go, how we should. So this requirement engineering, first phase, as we said, first initial step, this yields, this present a description of desired system. That means which functions, possible extensions, required documents, and the performance requirement. So functional and non-functional requirements. This includes the feasibility study, whether this problem can be easily solved. The resulting document of requirement engineering is nothing but the requirement specification. Then comes the design part. The earliest design decisions are captured in the software architecture. First, whatever we have to make, we make a software architecture. Like we want to make a building, then you don't start making a building. You have to make architecture of building. First, you have to pass that architecture. Then we decompose this into parts and components. What are the functions of and the interfaces between those components which are there in your software architecture you have devised in software architecture. And now you emphasize on what rather than how in this design phase. What? So the resulting document would be the design specification. Then we come to the third phase, that is the implementation part. So we focus on individual components here. Our goal is to make a working, flexible, and robust piece of software. But again, it's not a bag of tricks. So present day languages have a module or a class concept. Most of them are object-oriented, or previous one were module-oriented. Then we come to the testing phase. Do the software do what it's supposed to do? We verify, we validate. So are we building the right system? This is validation. Are we building the system right? That is verification. This is validation. This is verification. Validation with respect to the requirement engineering you have done. And verification with respect to the different phases which we have checked in. That are you making the thing right? Not the right thing, because the right thing is covered under validation. So start your testing activities in phase 1 on day 1. So testing can be started right from the first step. What about maintenance? Once you have delivered the software, you have made it and delivered. Now you will need to correct errors that are found after the software has been actually delivered. So now you need to adapt to the software to changing requirements, that is changing environments, platforms, OS, and various other requirements of user. So the global distribution of effort is the first phase, that is the requirement engineering, will take 10% of your time, design will take around 15%, coding will take 20%, testing almost 45%, some books say some other. Then some other book says 40% of time goes in maintenance. So specification also takes around 10%. The global distribution effort, that is rule of thumb, is 40-20-40, right? That is, the trend is to enlarge your requirement specification design slots and just reduce the test slot. This is the trend. But you need to see that the maintenance alone will compute or will boil down to, goes up to 50-75% of the total effort. This is very critical. There are various kind of maintenance activity, like corrective maintenance. In this, you correct the errors. Adaptive maintenance, that means you make your software to adapt to the environment, that is adapting to the changes in the environment, and this goes both for hardware and software. Then perfective maintenance, you are adapting to the changes present by users. So changing a user requirement, you make it perfective. So now this is the distribution of maintenance activity. Most of the time goes in perfective, that is user requirement, corrective because of error, adapting, and preventing. Okay. Next point is, now you are a tester and the product you are testing does not yet meet the testing requirement agreed upon in writing. So your manager wants to ship the product now. He has some pressures. So continue testing so that the next release will meet the testing requirements. What do? Discuss the issue with your manager. Talk to the manager boss. Talk to the customer. What you're going to do. These are options for you. Okay. Now you need to really think about that. We'll be answering these questions in our discussion later. So this is Hammurabi's code. Now the translation is, if a builder build a house for a man and do not make its correct construction firm, and the house which he has built collapse and cause the death of the owner of the house, the builder shall be put to death. Is it true with you? If it caused the death of a son of the owner of the house, they shall put the death of son of that builder. So, what Hammurabi's term issues were, you need to see that whatever you're making is going to affect lives of many people. Software engineering ethics, the principle are, first, you should act consistently with the public interest, act in a manner that is in the best interest of the client and the employer, ensure that products meet the highest professional standards possible, and maintain integrity in your professional judgment. Managers should promote the ethical approach, advance the integrity and reputation of the profession, and be fair to and supportive of colleagues, and participating in lifelong learning and promote an ethical approach towards your work. So it takes at least 15 to 20 years for a technology to become mature. So this also holds for computer science, like Linux, RDBMS, structured programming. Software engineering has made tremendous progression, I should say exponential growth. So we need to see and we need to work out. For the recent development, there is a trend in rising of agile methods. Shift is from producing software to using software. And now we have open source software all around. Success of this open source software has changed the things which we generally do in software engineering. And software development becomes more heterogeneous. What is the Agile Manifesto? The individuals and interactions over processes and tools. Working software is more important rather than comprehensive documentation. The customer collaboration is important than the contract negotiation. Customer has to be there. He needs to be present. And also responding to change or following a plan. So producing software rather than using software. That is, builder build pieces and integrators, they integrate them. We call them component-based development. So also the software product lines, we are available with the commercial off the shelf. So that means producing software now has taken place. Now let us use software employing all these. Now we are subjected to service orientation, web services, service-oriented architecture, open source or crowdsourcing. We can see that we have various software which are built. You can go to various softwares which are available to you, and if you find this example, you can easily get things what you require without even going to a company to proceed for the software engineering phases. So no requirements engineers needed. Give rise to a new business model in this case. Heterogeneity, we have introduced heterogeneity also. So in old days, software development developmental department had everything under control, but now teams are scattered in different parts of the world. The component are acquired from others, which includes the open source part, and services they are found on the web services. So now you need to think that which of the following do you consider as software engineering principle. First is you want to build with and for use, define software artifacts rigorously, establish a software process that provides flexibility, manage quality as formally as possible, minimize software components interaction, produce software in a stepwise fashion, change is inherent, so plan it, manage it. Trade-offs are inherent, so make them explicit and document them. Uncertainty is unavoidable, so identify and manage it. So, software engineering is a balancing act where trade-offs are difficult. Solutions are not right or wrong, at most they are better or worse. And maintenance is inevitable. There are many life cycles and they are all models. So this was the introduction session, and we'll be covering all these in greater detail in coming session. Thank you so much. Take care.